Well, good morning. I'm sorry it's 7 minutes late getting started for class. Math 237. Let me go over the announcements. A few today. Today's the 26th, is that right? Yeah. 26th. Our volleyball team, which is a very good volleyball team, or at least they were last year, I think they still are this year, on the 30th, which I think is that Monday or Tuesday? 27th, 28th, 30th is Monday. And we won't meet before then. They have a doubleheader that day. They're playing Coastal Alabama South, home meet at 4 p.m. Over on the Birmingham West Campus, Arthur Shores Fine Arts Building, which is our gym. And then at 7, they're playing Wallace State Selma. And that also, of course, is a home match. So anyway, that's coming up Monday, a doubleheader, 4 and 7. College Scholar Bowl is still looking, and for some reason, I haven't plugged in my projector, sorry. Today's been a weird day all day long. All right, there's Charles. Morning. Okay, finally got the projector working. College Scholars Bowl is still, the team is currently recruiting players with a knowledge of any subject, including history, literature, science, music, current events, mythology, and mathematics. So if you want to give a check on that, Mr. West is the coach, Mr. Matthew West. His office is in this building. If you go down this half flight of stairs here, go down the hall in between rooms 259 and 261 is his office, right directly in between those two. And then the NASA's Community College Aerospace Scholars Program will be receiving applications for this year's participation up until through October the 16th. I have several websites you can go to find out more information, eligibility, that kind of stuff. So I think you were probably sent, I can't tell for sure if you received this as well as others. So anyway, I'll be glad to forward that to you if you need more information, or you're welcome to look at that. All right, any questions on anything we've done up till now? I should have marked the roll before I started talking. Let me mark it now. Charles is here, and Keiston's here. Okay. Let me make this one other sort of a more personal, not school-wide, but just for me. Normally on Fridays, I have office hours on the Birmingham West Campus in the B building. B Hall is the academic building, room 226, I think it is. I believe that's the room number. No, B122. B122. Dr. Pruitt's office. Not tomorrow. Tomorrow, they've called a meeting for over here on this campus at 11 o'clock, so rather than waste time driving between campuses, I'm just going to come to this campus tomorrow morning at 8, and my office hours will be 8 till 11 tomorrow here in my office on this campus, and then at 11 till 12:30 or 1, we'll be in the meeting over in the Ethel Hall building. So I will not be on the Birmingham campus tomorrow. I'll be on this campus from 8 till 11. I'll be on this campus later than that, but I won't be in my office until I'll have to leave a little before 11 to make the meeting. All right. Any questions or anything up till now? Okay. We're in Chapter 2, Matrices, Section 2.2, Properties of Matrix Operations. We're on page 55 and getting ready to start example 5. Okay? Here are three matrices. Matrix A, 1, 3, 0, 1. Okay. Matrix B, 2, 4, 2, 3. And matrix C, 1, negative 2, negative 1, 2. Now, before we get going on this, just a little reminder of what we have been covering. We've been talking about ways in which matrix operations are similar to real number operations. Remember, associative property of addition, of multiplication, well, not multiplication, distributive properties. A few multiplication properties, are very similar. There are some things, though, that are very dissimilar. And I think this is one of those examples. So, what they want us to do is first multiply AC. Now, first, let me ask the question, can you multiply AC? Yeah. Now, don't look at B, but C. Yes, you can, because 2 by 2 by 2 by 2 is going to be a 2 by 2. Okay, AC now, not AB, AC. So what's the first element? Minus 2. Everybody see that? Okay. Second element? Second? Okay, are you going down or across? Down. Okay, that's fine. Okay, let's go down. Let's go down. 0 minus 1. Perfect. Okay. Then the 1, 2 entry, that way we'll know, be on the same page. 1, 2 entry is 4. And the 2, 2 entry? 2. All right, very good. Now let's look at BC. Can you do that? Sure you can. 2 by 2, 2 by 2. That's going to be a 2 by 2. 1, 1 entry. Second? 2. That will be 2 minus 4 is the 1, 1 entry. Is that what we're doing? First row, first column. 2 times 1 is 2. 4 times minus 1 is minus 4. 2 minus 4 is? Negative 2. Okay. I didn't hear the minus. Sorry.
I didn't say it the first time. I said it.
Oh, okay. Okay. What you want to do next? 1, 2 or 2, 1? I don't care. Go down or go across? I don't care. Pick one. Or go diagonal. I don't care.
No.
Which one you want to do?
Let's go across.
Across. Okay. The 1, 2 entry. What will that be?
It's going to be 4.
That'll be 4. Perfect. And then let's go down and do the 2, 1 entry.
I think it should be
Negative 1. Perfect. And then the 2, 2 entry is 2. Hey, look at that. A times C is the same as B times C. Got it? See, those are exactly the same. Okay? Does that mean you could divide out C and say that A is equal to B? Is A equal to B? No. Okay, no, you can't. Now, you could do that in real numbers. If 7 times 5 is equal to, let's pick something better, whatever. If two products equal each other, and you divide out any common factors, then what is left to be equal to each other. Not so with matrices. Generally, anytime you're multiplying matrices, throw out the rule books, okay? The things that work in real number system most of the time will not work in matrices. Occasionally they will, but not very frequently. So yeah, you cannot say because AC is equal to BC, which it is, therefore A is equal to B. You can't divide out the C and say, because guess what? We haven't even defined matrix division. In fact, I don't think there is such a thing as matrix division. So don't be dividing out matrices ever, okay? There's no such animal. All right. So AC is equal to BC, even though A is not equal to B. All right. Now, I say all that, and then we introduce a very special kind of a matrix. It's called the I sub n matrix. Have we introduced I matrices at all? I don't recall that we have. Huh? Identity matrix. I know you've had it before probably. Have we done it in this course yet? Okay. I think a couple of examples we did with one, but I told you it was an identity matrix, but here they're going to define it. We'll now look at a new type of a square matrix. These have to be square. You cannot have an identity matrix that is rectangular and not square. They have to be square. Okay? Here's what makes an identity matrix. The first element, upper left corner, 1. And then everything else in that row are zeros. Okay? In the second row, first element's a 0, the next element's a 1, and everything else in that row is a 0. The third row, the first two elements are 0, the third one's a 1, and everything else is a 0. Go on down to the last row, and you have 0, 0, 0, dot, dot, dot. Everything's a 0 until that last element's a 1. The key here is that the only non-zero elements in an identity matrix are 1s, and they're all on the main diagonal, the upper left to lower right. Every one of those is a 1, and everything else on either side of that main diagonal are zeros. That's your identity matrix. Okay? Now, here and that, when you do I sub n, now most of the time if you're doing identifying the dimensions of a matrix, like this A, you would say 2, 2, because it's 2 rows, 2 columns. Okay? If you identify them. But you see, with identity matrix, you only need 1, because it's got to be square. Okay? So this means there's n rows and therefore n columns, because it's that. In other words, you have n 1s down the diagonal, zeros everywhere else. That's an n by n matrix. So the nomenclature is I sub n. You don't have to say n or n by n, just I sub n, because it has to be square. So let's look at a few. I sub 1. What would that be? Make a guess. 1. That's it. Only 1 row, 1 column, only 1 entry. That's a 1. I sub 2. Okay. And what would be the elements? Second, 1, 0, 0, 1. Got it. I sub 3 would be 3 by 3. 1, 0, 0. 0, 1, 0. 0, 0, 1. That's it. Main diagonal 1s, everything else is a 0. And you can go on as many as you want. Okay? Now, so these I sub n's are your identity matrices for matrix multiplication. Now remember, we didn't have many things with multiplying that relate This is one that does. Just like 1 is your multiplicative identity element for numbers. Multiply any number by 1, you get the same number. Well, if you multiply any matrix, okay, by the appropriately sized identity matrix, you're going to reproduce the same matrix. So this is what they're doing in Theorem 2.4, top of page 56. Hang on, let me erase. All right to erase? Okay. Theorem 2.4. If A is a matrix, is an M by N matrix. Okay? Then the following properties are true. 1. A times I. Ooh, what size does that I got to be? If A is an M by N, what size does this I have to be? I's are always square. Say again?
Square.
And what size square? N by N, so you just put N, I sub N. And guess what that is? Identity matrix, A. Always A. Can't be anything but A. Okay, we'll see an example of that coming up. Second property would be, what if I multiply I times A? What size would that I have to be? A is an M by N.
So it's going to be N by N?
Did you say N or M?
N.
Okay, if you did an N, then this would be an N by N times an M by N. Can you do that? No. So what would it have to be?
N by N.
M by M. Okay, so yeah, that would be I sub M times A. And guess what that would give you? A, the same A. Identity is the multiplicative identity element. Okay, so let's do a few of those. Here's a matrix. 3 and negative 2. 4, 0. Negative 1, 1. Now, I want to multiply it by identity matrix. What size identity matrix does that have to be?
2 by 2.
Yes, it has to be a 2 by 2, so what would be the elements? 1.
0.
0. 0. 1. Perfect. Let's multiply and see what we get. Okay, what will we get? What size is going to come out of this? Why is that legal to do? This is a 3 by 2, and this is a 2 by 2. So what size comes out? 3 by 2. And what would be the first element there? 3.
And we're going down.
You tell me.
Vertical is going to be 4.
Okay. Yeah, 4.
Minus 1.
Minus 1.
Start from the top.
Yep.
2.
Negative 2.
Minus 2 and 0.
0.
And negative 1.
Not negative 1.
1. Yes,
1. 1. Exactly. Okay. And there you have it. Guess what? A times I, right size I, is equal to A. You just reproduced the A. You see that? You realize you did that? It's exactly the same matrix. Because that's the right side of identity matrix. Okay? Now, let's do, I've written too big. I'm going to have to clean the page. All right, you clean it?
Yeah.
Okay. Now, I'll multiply on the left by identity matrix, but I haven't figured out what size yet. So I'll multiply it by negative 2, 1, 4. What size identity matrix do I need to put here? Three by 3. So what would be the elements in that identity matrix? 1, 0, 0, 0, 1, 0. Whoops, I can't write. 0, 0, 1. Let's multiply and see what you get. Oh, what size do you think we'll get? What is the size of the right-hand matrix, which is also called the column vector? 3 by 1. So you can multiply because those two 3's are the same. And what answer you get? 3 by 1. Do the multiplication. What do you get? -2, 1, 4. Ding! You just reproduced it. You also knocked out the y. Okay. All right. You see how that works? See the math works? All right. Now, if you are, and this is a totally new subject here, just popping out of the sky, has nothing to do with what we were just doing, or hardly anything to do with it. It just, here suddenly. For repeated multiplication of square matrices, use the same exponential notation used with real numbers. So this is a totally new thing. Okay, now first, A has to be square. If A isn't square, you can't do this at all, okay? But if A is square, you can multiply it by itself, right? If A is any rectangle, can you multiply it by itself? Give me dimensions of a rectangle that's not square. 3 by 4. Can you multiply this 3 by 4 by itself, which is a 3 by 4? No, you can't, because this is 4, that's a 3. So you can't do a rectangular matrix by itself, but you can a square matrix, right? Okay? So, A has to be a square matrix, okay? Now, A by itself you could write as A to the first power. That's okay. All right. Remember, A is square. Since it's square, you can multiply A by A. And that'll also give you a square matrix same size, right? And that you can call A squared. Okay? They have to be square for you to do this. And A times A times A would be A cubed. Okay? And you can go on up. A to the kth power is A times A times A times dot 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 times A, as long as you have K A's there. Okay? So that is what A sub K, A raised to the kth power would be. Okay? Now, here's another rather strange thing. What do you think A to the 0th power would be? Second? I can't hear you. Yes, you are. In which size identity matrix? Whatever size A was. So they don't list it here. So they say I sub n if A is an n by n matrix. Okay. Has to be square or else you can't even do it. All right. Now, because of that, you can do some other things that you do with numbers as well. What if you have A to the jth power times A to the kth power? Can you multiply those together? And what will you get? J plus K. Perfect. Just like you do exponents of numbers. Okay? And how about this one? If you had A to the jth power and you wanted to raise it to the kth power, what you reckon that would be? A to the j times k power. Yeah, exactly. You multiply the exponents, just like we did with real numbers. Okay, as long as J and K are non-negative integers. Let's not throw any fractions, decimals, or negative numbers into it. Keep them positive integers. Okay, so with that as a foundation, let's go to example 7. Here's a matrix A. 2, -1, 3, 0. And what we want to do is figure out what A cubed is. Can you cube A? Can you raise A to the third power?
Yes.
Why? It's square. Okay, perfect. Now, when I make the little square here, have you heard this before? Okay. When I was growing up, I had an older brother. We were 2 years apart, but from early age, I was almost as big as he was, and then from later ages, I was always bigger than him. But we were always like best friends. I mean, we just did everything together a lot. Well, up until high school type stuff, then we drifted apart. But, growing up, we just did, we were each other's best playmate and that kind of stuff, But then 3.5 or more years later, my younger brother was born. Since I was big and Mike, we were together and he was just the runt, So we didn't do that many things together, but we did some. We played together all right. We didn't fight or anything, but he was just always a little kid, and we were bigger and older and stuff. But then about the time, and Mike was a pretty quiet guy, fairly serious, introvert, stuff like that. And I was not far from being the same. And we both did pretty well in school and that kind of stuff. Well, along came Dan, the younger brother. And he just wanted to make his own mark. And since we had already made our mark by being pretty good students and pretty quiet and that kind of stuff, he's going to be the opposite, okay? And number one, he's an extrovert. He has to be around people. Neither Mike or I really, we're okay with around people. Mike really doesn't like people. I get along okay. But Dan had to be around people. He was always out spending the night with somebody doing this and that. So along about high school years, he gave me a nickname. It was L7. Now, of course, that makes a square because that's what he considered me, a square, And up until, I don't know if he still calls me this anymore, but for years and years and years, he just shortened that from L7 to L. So, hey, L, I was just L. I think he had even forgotten what the L7 stood for. I was always L, so nothing to do with my name. So every time I get that symbol of a square, I think, I'm L7. Okay, I am a square, okay, and proud of it. Okay, so what would A to the third power be? Now you might say, oh, is there some simple little rule for what you can do to the elements there? No, there isn't. Okay, no, there isn't. You have to do a matrix multiplication. So let's start with 2, -1, 3, 0 times 2, -1, 3, 0. And do that multiplication, and what do you get? It's going to be a 2 by 2, of course. And what will that be? 1 for the first element. Tell me if you're going down or across. I don't care. Down, okay. 6. Now back up to 1, 2 entry. -2. And the 2, 2 entry would be -3. So this, by the way, is A squared, all right? Do you see any pattern there? Nope, there is none. So the only way you can get A cubed, I was going to say L cubed, okay. A cubed is multiplied again by 2 minus 1, 3, 0. Okay? And of course that's also a 2 by 2 by 2 by 2. It's going to be a 2 by 2. So let's start with 1, 1. What do you get? Yep. Is it 4 or minus 4? Okay. Next, are you going down? 3. Negative 1.
6.
Isn't it negative 6?
Oh, yeah.
Yeah, negative 6. Whoa, come back here. All right. See any pattern? Nope. None whatsoever. There's no shortcut. You have to multiply every one of the matrices out. So you can't say, oh, you take each one and raise it. No, that won't work. Because matrix multiplication is a lot more involved than just raising powers. Okay, let's see if we got the same thing they did. Negative 4, negative 1, 3, negative 6. Got it. All right. So that was just sort of stuck in there. And now they go back to other stuff. In section 1.1, you saw the system of linear equations must have exactly one solution, or infinitely many solutions, or no solutions. None that have 7 solutions only. No. 1, infinitely many, or none. Okay. And it says you can use matrix algebra now to prove this. Really. Okay. This is one of Keyston's favorite things, the proofs. Okay, good deal. All right, so here is theorem 2.5. We're just going to state it. I'll let Keyston prove it. Okay. For a system of linear equations, well, we just said that. Okay, theorem 2.5 is what we just said. For a system of linear equations, precisely one of the following is true. System has exactly one solution, infinitely many solutions, or absolutely no solutions. No other choice. Okay. Is it worth looking at this proof? Well, it is, because it gives you a method to use to do it. If they say, as they say here, if the system has exactly one solution, there's nothing to prove. It just has that solution. If it has no solution, there's nothing really to prove. It just has no solution. But the other thing is, does it have 2 or 3 solutions, or does it have to be infinitely many solutions? So you assume that it only has 2. Not 1, not 0, but 2. Okay? And if you can prove that that doesn't work, then you can show that it indicate that it has to have infinitely many. That's their process. I don't think it's worth it to do it. Let's go to a new kind of concept, and this is the concept of transposing a matrix. Okay? Oh, and there is a discovery first. But let's define it first, and then we'll come back and do the discovery. Okay? The transpose of a matrix, okay, is formed by writing its columns as its rows and vice versa. Okay. Either way you want to say it. So let's say A. Now A doesn't have to be square anymore. It could be. It's perfectly fine for it to be. Let's just say it's an M by N matrix. What do you think the size of its transpose would be? And we indicate transpose by A superscript T. Just like we did superscript numbers before were powers, this is a superscript T. What would be A transpose? What size would it be? N by M, because you made all the rows columns and the columns rows. So since you had M columns and N rows for A, now you have N rows and M columns for A transpose. So first, there's the size, okay? And here's what it would be. Here would be matrix A, our typical matrix A. A11, A12, A13, dot, 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 A1, N. It has N columns. A21, A22, A23, dot, 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 A2, N. A31, A32, A33, dot, 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 to A3, N. And we'll dot, dot, dot that on down and get to A sub M1, dot, 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 down to A sub M2, dot, 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 down to A sub M3, and we'll dot, 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 and dot, 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 and everywhere dot, dot, and we'll get to A sub M N. Okay? Okay, let me get my brackets to look a little more fitting here. Okay, that's matrix A. What you reckon A transpose would look like? Anybody? Start with A11. We always start with A11. What would be your next entry?
We're going A12.
We're going down. You tell me which way you want to go. Go down?
Yes.
Okay. Then that would be A12, A13, dot, 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 to A1N. You're absolutely right. Because your first row up here became your first column here. That's exactly what we've got. Going across, it would be A21, A23, dot, 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 to A. Wait, I didn't do that right. That's a 3-1. Oh, sorry. That's ugly. Ugly, ugly. Okay. A11, A21, A31, and this would be A M1. Because what was your first column is now your first row. You see that? And then they would continue like this. This would be A sub 2, 2. Now guess what? Your diagonal stays the diagonal. Main diagonal doesn't change. This would be A 3, 2, dot, 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 to A M2. And this would be an A2, 3, A 3, 3, dot, 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 up to A sub M3, and then a dot, dot, dot down to A sub 2N, dot, 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 to A sub 3N, and then we'll do dot, dot, dots in every direction here, and this will be A sub MN. You've exchanged your rows with your columns. The top one was an M by N. The transpose is going to be an N by M. That's what we mean by transposing a matrix. Okay. And yeah, I've already written what sizes they were. So now let's go. I'm not really going, but let me clear that. I should have asked if there are any questions. Let's do the little discovery first. Here's a little discovery. A is equal to, what are their favorite matrices? 1, 2, 3, 4. Pretty creative, huh? And B is equal to another square matrix, 3, 5, 1, minus 1. Okay? Now, first thing it says is calculate AB transpose. All right, now, I'll do it like they did. Put it in parentheses. What does that indicate you do first? You hope that the screen comes up. Oh, how has it gotten so dark? Has it been like that the whole time? Huh? It was off sometime, but is this the first time it's been dark like that? Okay, now, is it getting lighter now? Is it my imagination or? Weird. I hope my projector isn't getting ready to crap on me. Okay. Can y'all see that okay? Would it be better to turn off that set of lights? Would you see it better? Or fall asleep then? Huh? Leave it or turn them off? Leave it on? Okay. All right. Seems like it's getting lighter again. I don't know what's going on, folks. Sorry. So, what are you going to do first? Multiply the two matrices. So let's first figure out what AB is. Can you even multiply AB? Of course you can. There's both square matrices, same size, so you can multiply them, get the same size. So what's the first entry? Anybody? Five. Okay. Next entry, going down or across, I don't care. Tell me which way you're going. Second? Across. Okay. What's the second entry? The 1, 2 entry. Second? Did you say 3? Okay, I can't hear well. Okay. 5, 3. Perfect. Then do the 2, 1 entry. Anybody? 13, perfect. And the last, the 2, 2 entry will be? Was it 11? Is that what I heard? Yeah, that's what I got too. So if that's AB, what's AB transpose? Wait, can you transpose the square matrix? Sure you can. So what would it be? 5, okay, that one's right. 13 going across. 3 going down. And 11. Diagonals stay the same. Okay, good deal. Now, it also says to do A transpose times B transpose. So let's tell me first what A transpose is. Can you do that? Yay or nay? Sure, you can transpose any matrix. And what would A transpose be? Going down or across? Down would be?
3.
Nope.
5.
Wait. A transpose.
1.
1, got it.
2.
2. Okay. 3, 4. Okay. Exchange rows and columns. That's it. Right? How about doing B transpose? Can you do that? Sure, you can transpose any matrix. What would it be then?
1.
Transpose, you exchange rows and columns. You don't move any rows.
5. We exchange.
Okay. Exchange rows or columns. Rows for columns. So whatever was a row becomes a column in the same location. Okay. Hint, your diagonals don't change. Your main diagonal doesn't change. So if B starts with a 3, B transpose starts with a 3. Now tell me whether you're going right or down. I don't care. Down. What would be your down entry for B transpose? No, you don't go that far. You do this row, make it the first row, make it the first column. Right? And the second row, make it the second column. And there I put a minus sign. I don't know where that came from. Okay. Oh, it did. It did that this morning in the first class. There must be something, a connection going bad somewhere in here. Okay, this wasn't. Is that improving? No, it's not doing a thing. Okay, is it my, oh, it's a projector. Well, no, I don't know what it is. Okay. It's doing what it did before. Okay, we're over there. With B being 3, 5, 1, negative 1, B transpose is going down is 3, 5. Where? Okay.
We're in the,
Yeah.
we're in BT, right?
All right. Here's B, and we're doing B transpose. So what goes there?
1.
1. Yeah. And what goes below that?
Negative.
Got it. Okay. 1, negative 1. Okay. Hint, look at your main diagonals. They never change. See the 3, negative 1, 3, negative 1, 1, 4, 1, 4. And even in AB and AB transpose, 5, 11, 5, 11. Okay. The main diagonal does not change. Well, okay, well, wait a minute. If you had a rectangular matrix, obviously it has to change some, but all the elements that are there don't change. Okay. I guess I had to put a caveat in there. All right, so now we've done A transpose and B transpose. Now they want us to multiply that and do A transpose, B transpose. And can you do that? Sure, 2 by 2, 2 by 2. It's going to be a 2 by 2. And what will that one be? A transpose times B transpose. 1, 1 entry. First row of A transpose times first column of B transpose. What would that be? Anybody? Second? Okay, first. Oh, goodness gracious. Okay, this is getting old. It's coming back now, I think. I don't know which it is. Oh, that light is blinking there. What does that indicate? Is it always blinking? Status. I guess it's just being its own. I don't know. All right. I might mess things up here. About as good as I can do, I think. Okay? Depends on whether my glasses are on or off. Okay. What would be this entry here? Doing A transpose times B transpose.
He said earlier it was 5.
Okay. It's 3 is 18, right? So first entry is 18. Next, and you can go down or across, just tell me which. Tell me which. Down or across, I don't care. Across, okay. What would that entry be? -2. I agree. Next. -26. Next. -2 again. All right, we've done A transpose, B transpose. Okay. Now, it said make a conjecture here. Oh, one more. They say do B transpose, A transpose. Now, do I need to rewrite them? Maybe so. B transpose is 3, 1, 5, -1, and A transpose is 1, 3, 2, 4. Okay, so now let's do B transpose A transpose. Can you do that? Sure you can. 2 by 2, 2 by 2, 2 by 2. Do it then. Start with 1, 1. What would that be? Second? 5? Okay. Yep, 3 plus 2 is 5. Next? Down or across? Across. Okay. 9 plus 4 is 13. Got it? Next? 5 minus 2 is 3. And 15 minus 4, 11. What do you notice here? Okay. Rather bizarre but true. AB transpose is the same as B transpose A transpose. It's not the same as A transpose B transpose. B transpose A transpose is nothing similar at all to do with B transfer A transfer. But these two are the same. So if you multiply two matrices and then transpose the product, you get the product of the product of the transposes, but in reverse order. Since this was AB, then you get B transpose A transpose. This is AB transpose, B transpose A transpose. So you reverse the order and transpose each one, and you get the same result. It says select any other two square matrices and check the results. I'll let you do that on your own if you want to. That's up to you. Let us do example 8. All right to erase?
Yes.
All right. Find the transpose of A here. 2, 8. Does that have a transpose? Huh? What would it be? Written as a row, 2, 8. You're absolutely right. The column vector becomes a row vector in exactly the same order. Now remember what I said, sort of backing off from what I said, the diagonal elements are the same when you have a diagonal element. The only diagonal element you have is a 2, and that 2 is the same, okay, same place. The 1, 1 entry is the same in both. All right, let's do B. 1 1, 2, 3. Oh, this is a real creative one. 4, 5, 6. 7, 8, 9. What would be B transpose? 1 across 4, 7, 2, 5, 8, 3, 6, 9. Perfect. All right. Well, C. It's yes in Spanish. Okay. That would be 1, 2, 0. 2, 1, 0. I've lost it. There it is, 0, 0, 1. What would be C transpose? 1, 2, 0. Yep. 2, 1, 0. Wait, that's the same matrix. Did you do it right? Yes, you did. Yes, okay. Yes, you did do it right. Yeah, it was just to make you worry. And I did. Okay. Now, these are called, this one right here is called a symmetrical matrix. Because whatever your diagonal is, these happen to be all the same. They don't have to be. But then the opposite elements are the same. Okay. So that's called a symmetrical matrix. I think they also may call it a diagonal matrix. No, it's called symmetric. Okay. All right, symmetric matrix. I don't have room for D. Can I erase and put D in next page? Okay. Let's do D. Here we go. Here's D. 0, 1, 2, 4, 1 minus 1. Wait, can you have a transpose of a rectangular matrix? Sure you can. And what would it be? 0, I got that one. 2, 1, 1. Right. Now remember what I said before. As much as you have diagonals, they still stay the same. The only diagonal you got here is 0, 4, and that's still goes 0, 4 there. They don't change. The other things. This was a 3 by 2. Its transpose is a 2 by 3. Good deal. Any questions on transposing matrices? All right. Now, I think all the time we have left, we're going to spend on Theorem 2.6. It's basically talking about them, writing them down. I don't think we're going to have time to do anything more with them, but let's see what it is. Here is A and B, matrices A and B. Okay? Now, they put here, with sizes such that the given operations are defined. Let me just do appropriate sizes. That means whatever you're trying to do, you can do. Okay? It may vary from property to property, but whatever it takes to be right. Okay? And C is a scalar, as usual. Okay? Then the following properties are true. Here is the first one. Now you tell me what you think. If you take A and transpose it, and then transpose it again, guess what you get? Same thing you had to begin with A. You're absolutely right. It doesn't matter what size or anything that is. It's going to work. Okay? And that's called the transpose of a transpose. What a creative name. Transpose of a transpose. Okay? Number 2. What if you have A plus B and you transpose that? All right? Now, in this case, A and B have to be precisely the same size. Okay? So that's what I mean. Appropriate sizes, they have to be precisely the same size, whatever size they are. Okay? So let's pick a size for them. Give me dimensions for both A and B here. Pick 2 numbers. Say again? 2 by 2? Oh, you're really creative, aren't you? Let's have it be a 2 by 3, okay? Or 2 by 7. I don't care, but something other than just square. Okay, I'm the square. Okay, you leave me alone. Okay. All right. So what size you want them? Name it. Say again. 5 by 7, you said? All right, boy. Okay. They both have to be 5 by 7, so the sum will be a 5 by 7. Okay. What would its transpose be? 7 by 5. Okay. Now, this isn't proving anything, but just doing. So, it claims here this is A transpose plus B transpose. Well, what size would A transpose be? If A was a 5 by 7, B's a... A transpose would be a 7 by 5. And B, if that was a 5 by 7, its transpose would be a 7 by 5. You add 2 7 by 5 to a 7 by 5, you'll get a 7 by 5. Okay? So, at least the sizes work out, so do the elements. Now, how you go about proving this is do your AIJ and the BIJ, do those, and you'll see they work out. And this is called the transpose of a sum. Transpose of a sum. Okay? We're running, well, we're not out of time yet, but getting close. Now, 3. Okay. Has a C in it. What if you have C times A transposed? Okay? Remember what C times a matrix does? Multiply every element by that C. So guess what? It doesn't matter. Then when you transpose it, every element is still multiplied by C. So that's actually still the same as C times A transpose. There isn't any difference whether the C's inside or the C's outside. It's the same. And that's the transpose of a scalar multiple. Transpose of a scalar, I can't write, as if you hadn't guessed that, multiple. Okay. 4. We've seen this one, haven't we? AB transposed, anyone remember what that is? B transpose A transpose. You got it. Now, in this case, A and B can't both be 5 by 7s because you couldn't multiply them then. So they'd have to be something like one of 5 by 7, the other is 7 by 2, or something like that. Then you could multiply them, but then you would also be able to do the latter. And that's the transpose of a product. Transpose of a product. Not that you need to know the names, whatever. Okay. They're going to go about proving number 1, which is really the easiest one to prove, but you can read through and see how they prove it. All right. Now, maybe we have time for a little bit more here. Let's see if we can get it. Let's take property 2, and we're going to do property 4. So let me erase 3. Okay. Now we're going to extend property 2. What if you had more than 2? What if you had A plus B plus C plus D and wanted to transpose that? What do you think that result would be? A transpose plus B transpose plus C transpose plus D transpose. Yeah, no sweat there. Of course, all 4 of those have to be the same size, so you couldn't add them, and then they're yeah, that'll work. What if you have more than one, like A, B, C transpose? What do you reckon that would be? Nope. Start with the last one. C transpose times B transpose times A transpose. You just do them in reverse order. Whatever that order is, do them in the reverse order. If you had 17 of them out there, you start with the 17 transpose, 16 transpose, 17. You do them backwards. Okay? All right. Does that make sense? I do believe we may have run out of time. Have we? All right. So homework exercises here would be any of the odds 1 through 5. They should all be at calcchat.com. 7 through 11. They should be at calcchat.com. 13 should be at calcchat.com. Any of the odds 15 to 19 should be at calcchat.com. 21 should be at calcchat.com. 23 should be at calcchat.com. 25 should be at calcchat.com. I can't say them very fast. 27 should be at calcchat.com. Any of the odds 29 through 33 should be at calcchat.com. 35 should be at calcchat.com. 37 should be at calcchat.com. And I think you can do 39 or 41. Okay? So let's hang on to that, and we'll pick up the rest of those later. Though there are some fun ones in there, like number 51, you might want to look at that and see what you can figure there. But you don't have to do that now. Okay. Any questions? All right. One other thing, have a good weekend. Okay? And if you haven't gotten your research paper done, that'd be a good thing to do this weekend, wouldn't it? Yes, yes, yes. Okay.